In this video, we're going to go through orbital filling diagrams. So right now you're looking at the periodic table, okay? Have you ever thought and wondered why it's shaped the way it is? Like if you look on the left side, we have this part up here that kind of sticks out, and then we have this part up here that also kind of sticks out. So why? Why isn't it just a rectangle? Why are these big spaces between the rows here? Well, one of the things that we're going to explore in this unit is the arrangement of the periodic table. So the first thing that we're going to look at are some orbital filling diagrams, and these represent where the electrons exist when they orbit a nucleus. So here, for example, is a Bohr diagram of argon. So we've got 2 electrons in our first orbit. We have 2, 4, 6, 8 electrons in our second orbit. And then in our third orbit, which will hold up to 18, we have 2, 4, 6, 8. Okay, so hopefully that looks somewhat familiar. So we have what are called blocks on the periodic table. And we'll come back to this when we get into writing out electron configuration. But for right now, all you need to know are we have 4 different blocks. We have our S block on the left side of the periodic table, and if you notice, there are 2 spaces on each row. In the first row, we have this block here, and then this block here actually fits in right here. In the second row, we have 2. In the third row, we have 2. So every row has 2 spaces in the S block. In the P block, which is on the right side of the periodic table, you'll notice each row has 2, 3, 4, 5, 6. Each row has 6 spaces for every row in the P block. 3, 4, 5, 6. Okay. The D block, which is in the middle of the periodic table, each row has 10 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now let me just throw some numbers up here. 1, 2, 3, 4, 5, 6, 7. Okay. So if you look on the first row, we have 2 total spaces. Okay. So we have this space here, and then on the right side, which actually belongs on the left side, is helium. And if we go back to our Bohr model of argon, whoa, look at this. In the first orbital, we have 2 electrons. The second row, if we're counting from left to right, we have 1, 2, 3, 4, 5, 6, 7, 8. Whoa, that's crazy, because if you go back and look at the Bohr diagram, for argon, we have 2, 4, 6, 8. So every orbital kind of matches up with the number of spaces that we have on the periodic table. The problem is when we get to bigger atoms, like iron, for example, something kind of tricky happens. So same thing applies. So we have 2 in the first row. In our second row, our second orbit, we have 2, 4, 6, 8. Okay, so far, everything kind of matches up with our understanding. The number of electrons in each orbit kind of matches up with the rows on the periodic table. But when we get to the third orbit, something kind of goofy happens. So if we go back and look on our periodic table, on the third row, there are 1, 2, 3, 4, 5, 6, 7, 8 spaces. But if we go and look at our orbital filling diagram for iron, we have in the third orbit 2, 4, 6, 8, which matches up with the periodic table, but then we have these right here. So those are 2, 3, 4. We have 6 extra. And then why are these going to the outside if we haven't even filled up, or wait, well, I guess we have if we count all of the total electrons. But it doesn't match up here. So let's go back and look again at our periodic table. So something kind of silly happens here. the D block is always one row behind. So this belongs in the third row. But we can't shift the entire periodic table. We can't take the entire D block and move it up a row to match up with the third row, because then the number of protons wouldn't match. So remember, everything on our periodic table is ordered by the number of protons. So if we look at our periodic table, the fourth row, 19, 20, 21, we can't shift the entire D block up, because then magnesium, it would jump from 12 to 21 protons. So the arrangement isn't perfect per se, because, like I said, the D block kind of belongs up, but it doesn't because of the number of protons. So the rule that you have to remember on the D block is it is always one row behind. So even though this technically exists in the fourth row, it is part of the third orbit. I know that's a little backwards, and you're probably scratching your head right now thinking, what? So if we go back and look at our Bohr diagram, in our third orbit, we do have electrons that are in the D block. They exist there. So we fill up the entire third row here, and then we have some extra electrons that move to the outside that are part of the fourth row. So if you look on our periodic table, let's go back to here. So iron exists right here, which is in the fourth row. So we use these two spaces in the S block, but then when we get to our D block, we have 1, 2, 3, 4, 5, 6 electrons that we need to fill. And if we go back to our Bohr diagram, we have a total of 6 electrons in that D block. 1, 2, 3, 4, 5, 6. So those are where they kind of come into play. So if you're confused, that's normal. We're going to take this a step at a time, and let's just focus on orbital filling diagrams. So there are a couple rules that we have to follow when we draw these out. Okay, so the first one is the Aufbau principle. Electrons must fill lower energy orbitals first. So we have a mistake on our first row here. We skipped this. We have to kind of go in order when we're filling these. So if you notice, we went 1s, we filled it with 2, and then we skipped the second one and went right to the next block, which is the P block, to start filling. Can't do that. It's cheating. So instead, if we have a total of, it looks like 8 electrons, we have to fill them in order. Each box gets 2 arrows. So we fill this one, we fill this one, and then we have 8 extra electrons that we have to fill in. So we would move those over to our 2p block. Hund's rule says that all orbitals must be filled with 1 electron before electrons can pair. So in our first row, we made a mistake. Right here. Every space must be filled with 1 arrow representing 1 electron before we can double these up. So on the second row, if you notice, we have 2 electrons. We gave each space 1. So in order to double up, I would have to have 3 up arrows in that P block, and then I would go back and start to double them up. The Pauli exclusion principle states that only 2 electrons can go in an orbital, and they must spin in opposite directions. So in the first row, we have a mistake right here. When we're placing electrons into orbitals, we want to make sure that they're spinning the opposite direction, like this. Okay, so let's do an orbital filling diagram for lithium. Lithium is number 3 on the periodic table. It has 3 electrons. It's going to have 3 arrows. So when I draw these in, I'm going to always start at 1s. 1. I don't have another space for 1s, so I'm going to go ahead and put a down arrow, so that's 2. And then in 2s, I would add another up arrow. So I have 3 total arrows representing the 3 electrons for lithium. Next it says draw an orbital filling diagram for boron. Boron is number 5. It has 5 electrons. 1, 2, then we go to the next level, 3, 4, and then we go to the next level, 5. Draw an orbital filling diagram for sodium. Sodium is number 11 on the periodic table and has 11 electrons. 1, 2, 3, 4. Now watch how I fill the 2p. 5, 6, 7. Now I double them up. 8, 9, 10. I have 1 left. 11. Number 4 says identify the error in this orbital filling diagram for nitrogen. Nitrogen has 7 electrons, and we have 7 arrows. So looking at this, we didn't skip any levels, so we didn't violate the Aufbau principle. In the 2p, though, there's a mistake. We violated Hund's rule here. So every box should have gotten 1 arrow before we go back and double it up like we did here. All right, in this final example, it says identify the error in this orbital filling diagram for carbon. Carbon has 6 electrons, so it's going to have 6 arrows. So we started at 1s, okay, and then we skipped this. So here we broke the Aufbau principle. We want to make sure that we don't skip levels. So the correct way to do this would have been to, let's see, we have 4 electrons, so we should have filled this in first. And then with the 2 remaining electrons, we should have put 1 in this box and then 1 in that box. And that's how to do orbital filling diagrams.